Let's take a moment to talk about Newton's second law and how it's going to apply to circular motion. So let's pretend for a moment you've got a ball and it's in a circular track and it's going round and round and round in a circle. What happens if you cut that circular track? We cut the circular track, and now it's going to go, we'll cut it right here. So it's going to go right here, and it'll either go kind of at a curve, it'll go straight up, and it'll go over here. Will it follow path A, B, or C? Take a moment and think about it. I guess let's throw in another option too. We'll make this path D. Which way does it go? Okay, well the answer is B. And why does it go B? Well, it's going in a straight line. What's it doing right here? Well, it's going in a straight line. That's its velocity at this point, is going straight up. So if you take away the force, this track was pushing it towards the center. Right? The ball was bouncing on the track and hitting it, and the track was pushing it towards the center. If you take away the track, Newton's first law, it's just going to keep on doing what it's doing. In this case, going straight. So this isn't unlike what happens at a baseball game. So if we have a pitcher right here, this is our pitcher. He's a baseball player. Baseball players wear baseball hats. There we go. And we need a batter, because otherwise the pitcher does kind of a boring job. And we're going to throw this baseball. So the pitcher winds up, and the baseball is going... Right here's the point of release, and the baseball goes where the batter may or may not hit it, and, fun stuff. But what you'll notice doesn't happen is since the ball was going in a circle, it doesn't do this and keep going in a circle. It'd make the game of baseball really weird. Okay, so that doesn't happen. It just goes in a straight line. It takes whatever it was doing at the point of release, in this case, right here, and it keeps going with that velocity. It needs a force to change. So while we're on the subject of force, it's very important to know that centripetal force, not a new force. All the centripetal is just a direction. Just a direction. So you are looking at forces pointing towards the center. That's it. No new force, just all the old forces we know pointing towards the center. Let's take a look. Let's say that for some unknown reason, you are whirling a rock on a string above your head at 25 meters per second. Okay, so you're spinning a 12-pound rock a little over 50 miles an hour above your head. It's dangerous. Don't do this. But it's physics. You live for danger. So let's see what we can do. Well, Newton's second law, we always start off in the exact same place, sum of forces. Oh, except instead of x or y, we have this centripetal towards the center equals m AC. I said y, I meant C. That's the letter C. That's how the alphabet works. All right, so C is just towards the center. So if you remember, it's on a string, so that must be our good friend tension. So we've got tension as the force acting on it towards the center equals m. Oh, centripetal acceleration, well, that's v squared over r. All right, and that's it. That's all you have to do. You say, what force is going towards the center? Acceleration to the center is centripetal acceleration. And you just plug it in. So let's take this out again. Let's say we've got a car. So we'll put a little car right here. There's the car. And there's the driver of the car. And they're going on a curve. And the curve's going to go kind of to the left, but it's flat. So what forces are acting here? We've got gravity pulling down. We have the normal force pulling up because the car is not going into or out of the road. And then we have this force making it go in a curve. Force that wasn't there, this car would go flying off. Maybe something that's diminished when the road's wet. Well, it's opposing motion. It's our good friend, friction. So when you're setting this up, now we have a couple of directions. We'll set up a y-axis for vertical, and now we have I'll call it C for towards the center. All right, so two Newton's second law problems. We have sum of forces. We'll do y direction equals m a y. Is it accelerating in y? Nope, that goes to 0. That's fantastic. So the forces, we have n minus mg equals 0, and you get your normal force equals mg. All right, now we have normal force. Now let's look at this other direction. Let's look at towards the center. So sum of forces towards the center equals mg AC. Now, always, always, always work vertically, put all of your points that you're going to use. All of the parts use. Remember, you need this side of the equation and you need this side of the equation. Let's say our question, what are we looking for? Well, let's look for mu. All right, let's find what the minimum coefficient friction needs to be so that you don't go flying off into the abyss. Well, the only force we have to the center is friction equals m centripetal acceleration v squared over r. So now we know that this is mu n equals m v squared over r. I'm running out of room over here, so let's go this way. Right over here, we'll finish it. And we will say that n, so we have mu. N was mg equals m v squared over r. Oh, wait, that's weird. Mass cancels out again. Mass is going to cancel out a lot. That's one of the things we work for when we work with variables. So now we get mu is equal to v squared over gr. That's an r. That's kind of neat. Mass keeps coming out. Turns out your coefficient of friction doesn't depend on the mass of the objects at all. It just depends on what surfaces you have in contact. Kind of cool. So if you've got a fast car or a slow car, or a heavy car or a truck, doesn't matter. You're just worried about coefficient of friction. How do the tires interact? Now a weird case where you have non-uniform. So let's say this is a vertical circle. So this is, let's make a note of that. This is vertical. So right here we have mg, and here we have tension. So if we're at the bottom, again, same thing. Sum of forces, center equals m v squared over r. Let's go ahead and write that we are going to compare T, tensions in the string. So go ahead, take a guess or an estimate. Where would you think tension is going to be the highest, when it's at the top or bottom? So if we're at the bottom of the circle, we have tension minus mg equals mv squared over r. I'm going to write this as TB, or TB equals m v squared over r plus g. All right, if we're looking at the top, we have mg, we have tension, both pulling in the same direction. So sum of forces towards the center equals mac. Now notice, even though gravity is pointing down, all we care about for the purposes of this example is that gravity is pointing towards the center. So that is plus mg equals mv squared over r. And we get t at the top equals m. Make that equals a little better. V squared over r minus g. Which means that there's, no surprise, more tension when the rope is at the bottom than when it's at the top. Well, I hope that helps. I hope that illustrates a couple points. Please let me know if you have any questions, and I appreciate your time. Thanks, and I will talk to you later. See you in class. Bye.